we get to the probability part, I have to talk to you about what's called combinatorics. Combinatorics, big fancy name, is basically the study of how many ways there are to perform an event. Okay, so for example, one thing we're going to do here in a little bit is how many ways or how many different arrangements are there if I set people on the front row of this room, how many different patterns could we make? A bunch.
Isn't that the other summation point?
It can be, yes, depending on what the situation is. It does relate to those usually. We're getting there. So combinatorics, how many ways are there to do something? Or, okay, how many ways, how many different, if I was to take this room, how many different groups of 5 people can I put on the basketball court to play basketball? How many different groups of 5 people of you could I put out there?
A lot.
Out of this room, how many teams? How many different teams of 5 are possible?
67, 3,024.
Okay, great. How do you find that out?
Well, we're getting there. You just hang it. Hold on.
Hold your stuff, and we're gonna get there pretty soon.
Okay. But first, we have to learn what's called the fundamental counting principle. Okay, this is a big fancy name for a super simple concept. And this is principle with an LE. It's a principle on how to do something, not like the principle of the building. Okay. So I'm going to give you a basic idea. You decide you're going to start a little restaurant over here in the park for students to go over and get food at lunchtime. You know, little burger shack type thing. Okay. You're only going to serve hamburgers or hot dogs.
Why don't they let us out of school for lunch?
You don't have time. Safety, lots of issues. Okay, and with it then they have a choice of chips, French fries, or, okay, I want a third choice. What else do you want to offer as a side with it? Tater tots? Okay. Well, tater tots won, so okay. Okay. So, you serve these little combos. My question to you is, how many different combos are possible? How did you get that? 6. Yes. Thank you, Eric. Okay, okay, we're going to do it the way you would have done in elementary school. You would have gone, well, I could have a hamburger and chips, a hamburger and French fries, or a hamburger and tater tots. That'd be 3. Or I could do hot dog and chips, or hot dog and French fries, or tater tots. And that would be 6 lines that I just drew. But you all, being the wizard mathematicians that you are, already went, oh, there were 2 choices of a main entree. There were 3 side choices. And what did you do to get this answer?
Multiply it.
You multiplied. The fundamental counting principle says that to find out the number of ways to do something is you multiply how many of each type of thing there are together. So we multiplied and we got 6. Woo, doggy. That was a tough one.
That is a very So what we can see like how many times there is
So let me give you an example. A car manufacturer. They've limited down. They used to give way more options if you ordered a car. But okay, suppose we're manufacturing cars. And they've decided they're going to, whatever model car we're making, there's going to be 8 body colors you can pick from. 2 types of fabric for the interior seats. So leather and nylon cloth, whatever you want to call it, alright. And there's going to be 3 option packages you could pick from. You know, do you want to add this air conditioning, do you want a moonroof and this and this? What are your option packages you can pick from? It used to be you could pick everything each individually. They've kind of gone away from that. Now you have to pick this package, or this package. You can't pick the individual items you want anymore. Okay, so I want to know, how many different cars could they make to meet those situations? How many different? And how did we get 48? Woo, yeah, we did 8 times 2 times 3. So there's 48 different car looks, whatever you want to call it, we could produce from that one model there. If you have those different. And imagine if you actually considered all the different options that are possible. There would be a lot, yes. Okay, so the fundamental counting principle explains why on almost everything in this chapter you're going to multiply. There will be one place where we will add, but most of the problems you're going to multiply. And it's due to the lovely fundamental counting principle. But now, new big word. We love it. I want to talk about how many permutations of something are there. And the big question is, what are permutations? So let's see, what could you have just done? Okay, we'll take the cheerleaders. Okay. There's how many cheerleaders? 8? 9? 9? 9.5?
Yep.
We count Jenny in the half. I think Mariah's
Okay. So we're going with 9.
We counted Jenny in the half.
Oh, whoops, didn't want that big a print. Okay, so you have 9 cheerleaders. They're all going to stand in one line. How many different arrangements of the cheerleaders are there?
9 exclamation points.
Oh.
Okay. Permutations are ways to arrange things in patterns. Think permutations of a P, patterns. If they say, well, no, how many permutations of something, it's how many different patterns are there. So it's the number of arrangements or patterns that can be formed. So, some of you have done this, some of you hadn't, and I want to prove to you why this works. Okay, I've drawn 9 blanks. Why did I draw 9 blanks? Okay, there are 9 cheerleaders, all right. So when you go to pick the first cheerleader to stand in the first spot, how many choices do you have?
9.
Aren't there 9 of them? Okay, one of them stays there. How many choices are there for the second spot?
8.
Then there's 8 people to choose from, then 7, 6. Okay, and then what do you do with those numbers?
Multiply them.
The fundamental counting principle says that there's 9 ways to do this, and 8 ways to do that, and 7 ways to do that, and 6 ways to do the next spot. The fundamental counting principle says you multiply. Okay, now that's not a horrible thing to type in your calculator, but let's face it, if I made you do 20 down, 20 times 9 equals 18, that's just a little tedious typing that in your calculator. So mathematicians went read a better way, a shortcut way to write this. And yes, they said we're going to use an exclamation point, but it's actually called a factorial. That is 9 factorial is how you read that. If you see 9 exclamation point, it means start at 9 and multiply every single number there is down to 1. So if I said do 50 factorial, That's going to be a whopping huge number. Because 50 times 49 times 48 times 47, it does every single number until you get to 1. Okay? Okay, and so, now, the question then is there a quick way for us to do that on our calculators? And we certainly hope so. So, if I type a 9, the big question is, where did they hide the exclamation point? You can always go to symbols, but that's... Okay. Unfortunately, they're not always super duper consistent about where they hide these things. Dude, didn't even open.
Oh, I found it.
Oh, it's tiny. Okay, because you might think a lot of the common symbols are hidden under the pi button, but that's not one of them. It's in the book, but that's the slow way. The right of the G key. If you look down here,
I think you gotta get rid of the pi.
I think I do too. Escape. Get out. Okay, yes. Okay, it's also got, you can also program it. You can write programming code, so it's got symbols and questions. You can actually type whole documents on here. I can write an entire worksheet on this calculator and give it to you as a calculator worksheet. So, yeah, if you notice, most of your symbols, if they're commonly used symbols, yes, you can go to the book or all the templates. That's slow. Most of the commonly used symbols are either under the pi key, one of these keys on either end of your alphabetic keyboard. It's a very quick way you can hit your exclamation point and say, oh, 9 factorial. Yeah, that's 362,880 ways. So, cheerleaders, I expect to see you in different arrangements every single time you ever stand on the floor. And you need to keep track of what arrangements you use and not use, so then eventually you can produce the 362,880 ways.
Wow.
That's a lot, yeah. And that's just 9 factorial. Think about it. What's 50 factorial?
A lot more than
Okay.
Dude, I dare you.
These-
I dare you.
These calculators will do it. These calculators have much bigger memories. They will do it. My old calculators wouldn't do this, but these calculators will.
To get that factorial button?
This button right beside the G. Hit that button, and you'll see factorial. So, and notice there's still digits off the screen.
Mine has a bunch of zeros.
So,
how much of the difference
yeah, there's a lot of, I mean, it's actually quite a large, well, it's 50 times bigger, so, because you're multiplying by 50, so it'd be 50 times bigger, but, yes, that's a lot of digits, you're correct. So, but hey, it beats typing it in yourself, so you like that factorial key, it's your friend. Okay, that was an example of what we call a linear permutation. Why do you suppose that was linear?
Because it was in order.
Yes. You were arranging things in a line. Okay, so I'm about to give you a set of rules for how you do linear permutations. Okay. And I'm actually going to give you 4 rules for how you do linear permutations. These rules you won't find in a textbook, you won't find anywhere. They're just my logical organization of these, I guess. So, these are on the journal on the back side, about the second or third question down, maybe. So, if you are arranging all the objects in patterns, you're going to use all the objects you've got. In this case, we were using all 9 cheerleaders at once. If you want to do all the objects, then all you have to do is, however that many is factorial. That will tell you the number of ways to do it. So if you're doing all objects, it's n factorial. Okay, but what if I shorten it up? What if I want to take a smaller group chosen from the larger? So suppose I only want to do an arrangement of 6 cheerleaders chosen from the 9. Does that make a difference? said from a large group. Okay, so, well, let's think about this a second. Okay. Choose 6 cheerleaders from the 9. That's all I wanted there. Okay, so yeah, if I'm only going to do 6 cheerleaders, if I do it drawing the blanks to logically figure this out, I'd have 9 to pick from, and then there's 8 left, but am I going to go all the way to 1? No, I'm not. Okay, so can I use a factorial to do this then? Factorials automatically go all the way to 1. So I can't do 9 factorial anymore. Okay. Well, there's actually a special notation we use. It's called the NPR, what I call NPR. P stands for permutation. The first number is the total number of objects you have. And the second number is the number of objects you're going to use. So in this situation, how many total cheerleaders do I have? I have 9 total cheerleaders. I'm arranging them in patterns. So I'm going to do P for permutation. Okay, but how many of them do I actually want to use at a time? I'm doing 6 of them. So we would write that as 9P6. Okay, now I'm going to show you what your calculator does, or how you work it with factorials, but then your calculator actually also has this built into it. If you work it with factorials, what your calculator does is it goes, oh, there's 9 total factorial, and then it subtracts the 2 numbers, which in this case would be 3, and it does divides by 3 factorial. Now, why does that work? Well, if I write this all out, oh, get rid of space. Over 3 times 2 times 1, what's going to cancel? What cancels? Oh, sorry, I thought you were, okay, no, didn't realize that you were answering that. And notice, what's left? The 987654 that we wanted in our blanks right here. So what it's actually doing, if I give it to you in formula form, what it does is it's doing n factorial, the total amount you have, and then how did I get the 3? I did 9 minus 6. So in terms of the letters in this formula, I would have to do, subtract the 2 letters would be n minus r factorial. That's how it's actually calculating that for you. So, soluble people, they like to answer questions like that.
Can we say
Calculate 7p2, and you don't have a calculator with you, so you can't punch the fancy key that will do it for you. They want you to know that, oh, it's 9 factorial over 7 factorial. Yeah. So they want you to know that that's how it's actually calculating it. Okay. You, however, can do it in your calculator. The question is where. And this is one of my disgusting things that I'm not happy with this calculator about. My old calculators wrote it just like that, 9p6. This calculator, they switched it back to the other notation, which I find students confused more, so I'm not so thrilled that they switched it back. But where you suppose you ought to go to look for this? It's not in any of these special keyboard notations. You actually have to go to menu. Okay, probability, number 5. And notice, it's got permutations and combinations. We haven't learned combinations yet. But yeah, it's got permutations. Oops, what did I just hit? Did I just lose it? Brad. Menu, probability. Oh, shoot. I had my cursor up somewhere. Who knows where my cursor's at? Okay, one more time. All right. This is what I don't like. Instead of, they could have left you little boxes and you could fill in the N and the R yourself, but they didn't do that. They write NPR and then they write a parenthesis, and they want you to put in the parenthesis the two numbers that you want. So in this case, we were doing 9 things, but we were only choosing 6 cheerleaders at a time. So you have to put a comma in, and your comma is where? Yeah, clear the bottom left corner. Pi. You have to put 9 comma 6. I like that. On the old calculators, we could fill in the N and the R on either side of the P. It worked perfect. I do not know why they changed it, but I'm not thrilled about it. And so there are 60,480 ways we can arrange 6 cheerleaders. That's a little more feasible you could do in your lifetime.
That doesn't even seem to make sense.
What, in what way does it make sense?
Like, I don't know, it just seems like too big.
I'm way over time.